that's what kind of very interesting application during that time, and we found, okay, this seems a good adoption of the AI. However, the bad thing is that after the paper published, a lot of people really come to us and say, okay, whether you can apply this thing to the real world setup and help us to find zero days. And then we said, okay, since the result is pretty good, and we tried out, and but the result is really bad. And after going to this kind of bad cases, you can easily understand why this thing is not going to work. Because what we're doing here is that we use the syntax, the structured information of the program to train a neural network. But the intention is to find the vulnerable program, which is where you're talking about the runtime behavior of the code. So you learn something from the syntax, and then you hope this classifier is able to identify the tiny, subtle semantic difference between a normal program and a vulnerable program in the semantic level. This is not possible because there is a potential a big gap between the syntax and the runtime behavior. So this is the kind of I think the fundamental reason this you can do it well in this kind of the well-defined kind of data sets. That could be potentially an overfit. But you bring some like unknown smart contract, unknown code, this thing cannot be generalized. So this is the kind of the very natural result you are going to expect it when you're adopting this kind of solution. So this gave us kind of very, even though I think this is probably one of my best highly cited kind of paper, but it's actually not a good example. But this also triggers us, okay, how can we should really apply AI in this setup, right? And then the ChatGPT came out end of 2030. And during that time, there's another kind of interesting debate. Many people think, okay, this problem is solved. Okay, so this cannot do it, but large language model is very smart. You throw whatever smart contract and program into the large language model, and they will tell you whether it's vulnerable or not. And then the kind of industry thinking, okay, security auditing company, they're doomed. They're not no more business. But very soon, like after 2 weeks, security company all came up and demonstrated experiment to say, okay, ChatGPT has so many false positives and so many false negatives in terms of vulnerability detection. Is simply because of the same reason. Large language model is just another neural network which is trying to understand the syntax. The training is based on the syntax, and vulnerability is still a semantic thing, right? So you know that it's just have a kind of better probability. Maybe they see more vulnerable functions, but if you tweak one character in this kind of code, you turn a non-vulnerable function into a vulnerable function. I don't think the large language model can tell you the difference. So this is the kind of the result we're expecting, and this shows whatever kind of model you're using this kind of training kind of approach is not going to work. So this is things we call it kind of data-driven approach. What I told my students, okay, the data-driven approach is not going to work. But now the question is how to make it work, right? So if large language model is not able to do it, how can we make it work? So after that, I think beginning of 2024, we start looking into a different kind of idea. So this is a paper we published last year, and the idea is that we turn this kind of data-driven approach into something we call knowledge-driven approach. And the idea is that we want to simulate how the hackers think when they find vulnerability and digitize that steps into a number of components in the flow so that we can try our best to simulate how the hacker thinks and turn that into some kind of automated algorithm. And the idea is not difficult, okay? When I gave you a piece of code and I ask you to find vulnerability, the first thing you do, you look into the code and understand what are the useful information, what are the relevant functions with the vulnerability, right? The other things, supporting libraries, supporting code, you can get rid of. So this is kind of planning, identify the candidate function, and after that, you zoom in to a particular kind of code to say, what is this code is doing and which variable potential can have vulnerability. You're going down to inside the details, and this part we're using large language model. And after that, you have the candidates, we do the kind of validation to see whether it's a real vulnerability or not, by using traditional static analysis, or you can even use runtime analysis. And the whole process is more or less following all these kind of security auditors kind of steps. And this turned out to be really, the result is really well. We are able to achieve like around 70% F1 score. If you ever know any of the traditional static analysis tools, the F1 score is around 10 to 20. Simply because the traditional way have too many false positives and the report is so long and you are giving all these kind of useless kind of candidates. So the security is, the developer is fed up by this kind of report. They never use this kind of tool. But when you have something like 70 F1 score, which means that you are reporting mostly the true vulnerability. And not only that, I think we commercialized this tool already. I think today, I think you can start to think whether we have more users starting using this. I think this gave us a really good feedback that this kind of agent idea is going to work. But here we're not using large language model as kind of one black box solution, but we turn the black box into a very clear white box step. And which step works, which step doesn't work, we have the kind of transparency. And the key thing why this process cannot be done before. The key, I think, the observation is that the usefulness of large language model is actually on this step, which is trying to summarize and comprehend the code, which we cannot do it before ChatGPT. You're never able to build something to summarize whatever code the developer writing, right? So even though this process is well known, but you cannot easily digitize it. But after large language model, then that help us to improve this kind of adaptability of this kind of flow in kind of real setup and make it more automatic approach. So this is, I think, is a very good kind of I think lesson we learned, and we want to say, okay, so since this is working, and how can we make it even more generalized? So this work we support only 10 different kind of vulnerability types. So we want to support more, but you need to also go through this the flow. So we think, okay, how can we improve the situation? So that led to the second paper we published this year in the UK conference. And in this work, we adopt two different kind of ideas. The first one, we introduced this multi-agent kind of concept, because when the security company, they do the auditing, they typically have a team. So the same contract may be audited by the two different persons. The reason for this is they want to reduce the false positive and false negative. Right, so they don't want to make the mistake. So simply we adopt that to set multiple roles. We have one critique to help you to double check whether it's a correct vulnerability. That's one thing. Second thing I think is also quite interesting. We introduced a trust LLM. The idea is that we want to learn quickly how the security expert can find different vulnerabilities. So we get a number of smart contract auditing report and fine-tune the large language model with this report so that this large language model is able to see more kind of different type of vulnerabilities so that it can become more generalized. So these are the kind of two things we introduced in this work, and we pull up the accuracy from 70% F1 score to 90 something. And then that makes the whole thing really, I think, impressive. So that's why this paper got published. But after this, I talked to students, I'm not really happy. The reason is that even though the whole thing works, but the so-called trust LLM for us, for me at least, it is still a black box. Because you want to learn the knowledge in smart contract, but you do a fine-tuning. And after the fine-tuning, you don't really know whether the large language model is able to pick up the essence or this kind of correct details for different kind of problems. So this for me is still a black box, and the results we're not able to really have that kind of confidence and guarantee in the results. So this is not something I want. And so I told the student, okay, we need to think about this. And let's lead to the third kind of work. On the same topic, we make it like the third time. I think this time, I think we make it right. And the idea is we don't believe the large language model is able to solve a problem, but we want to make sure we are able to extract the precise knowledge from the auditing report by doing all this kind of NLP technique, and eventually we generate this chain of thoughts and make this as explicit step as possible, and then confirmed by the security auditor. And after this, what we have here is the distilled real knowledge from the security kind of expert's mind. And that really helps us to get the correct and transparent kind of understanding from the human brains. And then after that, we simply just apply the learning model and replay this kind of the chain of thought, right? So this is the things we did, and this is the kind of solution now commercialized in our product, which I think based on the very recent feedback from the security auditor, he is really impressed. He didn't believe all this magic, but now whatever contract he audit and using the same tool, I think now we still have some gap in the kind of multiple contract when you have a kind of interactions. So that is something we're trying to do. But for the single contract, the accuracy is really comparable to the human beings, right? So this is the kind of very, very exciting things we got along the way. So this actually gave us a kind of feedback that this kind of agent idea really works. But the key thing is not about the steps, process, or whatever agent thing. I think the key thing really bring the value is the knowledge we extracted here, right? So that is, I think, the good things. So we get this thing down. So simultaneously, we're trying different kind of ideas about the agent things. So this is another slightly different topic on the driver generation. I'm not sure how much you understand this, but this is a very important bottleneck Google Cloud team is facing. They are doing massive amount of vulnerability detection for the open source libraries. They have everything, and platform and money and everything. But the missing part is that they need the community to contribute to the flooding drivers in order to run the flooding testing. So this is the kind of big bottleneck. So then we say, okay, whether we can automate these things. And this is the first attempt that we have on this document for open source library. Then we write a prompt and ask learning model to generate a kind of drivers, right? So in this way. And the overall, the result is not bad. We are able to achieve something like 64% of accuracy in terms of flooding driver generation. But this is first version. This is more like a simple ChatGPT version. We're just using the kind of code generation capability of the learning model to generate flooding driver. But we have another paper published this year to do a multi-agent version of this thing, right? And that gave us a much better result. So this is, I think, another scenario which turned out to be quite positive. And we did another thing. This is also on smart contract to do the kind of property generation. When you fight to do the verification of smart contracts, sometimes you need to have the security property. But security property is difficult to write because you need to be a security expert in order to write a security property, right? So, but most of developers, they don't have this kind of knowledge. So what we are doing here is a very simple idea. When you have the smart contracts and the security property on some existing code, we extract that and teach a learning model. And then when the learning model to see another similar code, then it's use this kind of in-context learning capability to generate corresponding property. And after that, then we just run the traditional execution, and then we can find the bugs and vulnerability. So this is actually a very, very simple idea because I think it's a very good adoption of the formal method in the security analysis. And we not only publish the paper, but also get a paper award, which I think we are very happy. But I'm not satisfied with this because this is, for me, it's too simple. This is more the kind of ChatGPT things. So we have a new version of this thing we call the property agent. This is not the property agent we want to rent a place, but this is the property agent to generate interesting security property. And the whole flow, I don't want to dive into details, but the whole flow of this one is actually very much similar to the human security expert, how they write the property. Okay, you understand whatever the functionality of the smart contract and security requirement attached to that, and then you build this knowledge graph. Then we saw it somewhere. And after that, when you have new contract, we do all this analysis and try to understand what exactly this smart contract is doing. And then we map the functionality with the things in my knowledge graph. And then based on the mapping between this function, have this kind of property, then we reverse to generate the corresponding property for this contract. So this is really like it's trying to simulate how the security expert is doing in a manual kind of approach. And I think this result is actually much better than this paper we published. So now we are trying to wrap it up and submit another paper for this. But all of this you can see is actually very much kind of human simulation kind of ideas. So the more or the more precise you can capture the knowledge, the more direct translation of knowledge into the agents, and that gives you the better result, right? So this is things we tried. Of course, there's pen testing GPT, this paper published, and now we're working on pen testing agents, so I'm not into detail. This, I talked quite a bit about vulnerability detection. So the second topic I want to highlight is on the repairing part. I think this is also a very interesting journey and story we've gone through. I really want to share with everyone about the AI adoption kind of experience, right? This task is to see when you find a vulnerability, you want to patch it, right? We want to patch it automatically. And the first attempt is that we want to ask ChatGPT, give me a buggy code, you generate a patch code. And if you ask ChatGPT to do it directly, the result is very bad. And the reason is very easy to understand because the large language model is trained with the code only. You will never train a code GDP or software GDP with the patch information. Right? That is not in your training data. So if you have something the large language model never see, and they will not able to generate patch. So this is very logical. So in order to enhance the ChatGPT with code generation capability, what we did in the first version of the work is we just got this bug and fix tag. Very simple. We got the vulnerability and the vulnerability and patch. We got the pair, and then we fine-tune a large language model. And after that, the large language model has the matching between the vulnerable code and patch. Then it will generate the patch, right? So the idea is very simple, and of course we can beat all this existing large language model, and we managed to get this paper published. And we are also very lucky to get a paper award for this paper is because during that time, people still figuring out how to apply large language model, and we are already starting how to do the fine-tuning. So the reviewer is fascinating about the fine-tuning technique, so they like all this approach very much, and overall the things works. But for me, I'm not happy. The reason is that this goes back to this kind of data-driven approach. I have no clue and no confidence about the patch this approach generated. There's no explanation, no transparency. And this is the whole, based on this, is a black box thing. Right? So I told my postdoc, I'm not happy about this. It's not transparent, it's no explanation. And this guy is very smart. He said, okay, you want explanation? Okay, I will do it again. So we published another paper in the 2024. And the idea is that this guy is very smart. He added vulnerable code, add the patch code, and also add explanation for the vulnerable code, and add explanation for the patch code. And then he put all of the things and do a fine-tuning. And then the large language model will not only generate the patch, but also generate explanation for the patch, because he has the training data. Right? And this result is pretty good, so he managed to publish paper again. And he told me, hey, Professor, our paper is published, but I told him, this is not something I want. I want explanation. This is not the real explanation. This is the memorization. There's no true understanding about the problem. I want an agent. I don't want a kind of data-driven approach. So this is the things I showed to him, and he finally listened, and he come up with a repair agent, and I think this time it is correct. Okay, the repair agent essentially is adding a kind of mapping between the root cause analysis of the bug and the solving strategy for this root cause. This is how the humans start to fix bugs, right? After you see certain bugs, you understand that this is the kind of bug you can use this way to patch it. So what you solve is really the problem definition and solution of this problem. And if you have this, and then you apply the solution in the context of this particular vulnerability or particular bug, and then that can really help you to give the clear explanation, because this is the root cause, I know it because I have done the mapping, and this is solution based on my previous experience. And this is actually how human beings are fixing bugs, right? Especially when you become an experienced kind of security expert, you have actually a deep understanding about the root cause and the fixing strategies. And it's very lucky we just got the acceptance news this morning on the way to UCL. So now I think he's happy finally we have gone through this kind of transferred from this data-driven approach essentially to this kind of knowledge-driven approach in terms of this bug repairing kind of task. So after done so many different kind of things, I think the interesting things for us is no longer just apply agent or build agents. This demonstrates it's working, but I'm interested to see how to make these things more systematic. Then we start looking into the architecture of the agents, and this is actually a very popular diagram which people are now more or less following, talking about you have agents, you have memory, short-term memory, long-term memory, planning action tools, which seems reasonable, and we want to start using this to build some kind of agents. And this is more the kind of security analysis agents. I think John is working on this, and this is actually very complicated. We really want to categorize the different kind of vulnerabilities, and for each of these vulnerabilities, how to bring the domain knowledge and how to bring build all these tools, which are like the arm and legs, the MCP tools. When the people find vulnerability, what are the tools they're using? We're adding that, add the kind of MCP libraries into the agent so that they can also simulate all the human behavior, right? Which I think is a very important thing, and we hope that this can be converted to different kind of vulnerability detection tools, and we can sell for money. So this is the things we're doing, and after the success of this, we're starting working on the different agents. Vulnerability detection we have done, binary SA agent, so this is for to understand open source for the binary code. Malware analysis agent we just presented to network defense last week. This is something we are working with the collaborator. We are building solutions. This one is APT we have done. Anomaly traffic detection we are working on. These are some kind of new topics we want to do. Essentially, we want to re-look all the cybersecurity research and do it again with the kind of agent, which I believe you will beat all this previous workflow, right? Because this is kind of true kind of knowledge. But to be frank, to do each of these tasks, public paper is one thing, but to do it well is really, really difficult because it's not only about AI agents. The most important thing is about deep knowledge about this particular task, which is actually very difficult for most of the students to get. And I asked my students to work on the agent write paper, they have no problem, but when I ask them to find the vulnerabilities manually and figure out the knowledge and behind things, this is actually difficult because the security expert took years, right, to accumulate knowledge. So to solve this gap between the research and security industry, I did a trick. I hired a top hacker as a PhD student, and I asked him to digitize whatever in his mind. And if he can do that, then he can graduate, right? And this is, I think this guy is very smart, and he just submitted a paper last week, and he is going to start his PhD in August this year. So this seems that I think this kind of strategy would work. It works. So these are some more concrete things I don't want to talk about, but I really want to share that we have gone through the journey about all the kind of data-driven approach to the knowledge-driven approach, and to a state that we know how to effectively build agents. So this is still the first generation of the agent, but I think this software engineering, I will talk quickly. So this is another set of agents we want to build to automate software development. If you probably heard about this, all the hypes, right? The Cursor, the Windsurf, the white coding, Labo, these are very hot kind of company nowadays. People talk about code generation. And we're doing something similar, which is trying to, but it's not just generate code. We want to do this kind of end-to-end software code kind of development. So we have a requirement agent, architect agent, coding agent, testing security agent, and even a code verification agent. So that we hope we can have a program manager agent orchestrate all of them to generate software from end to end, and with certain quality control so that this can really be deployed as a commercial solution. So this is kind of very ambitious things we're doing, and I think we have built this kind of requirement agent since working well, and now we want to connect them so that we can really, these three agents are done separately. Now we want to connect them to really generate comprehensive code. Right? So this is things we're working now. And not only the forward way, we also work on the reverse way, right? So we want to build a reverse agent to really understand the program. Because this is a very important thing. Currently, ChatGPT, they have linked the ChatGPT with GitHub recently. So this is a big thing because you are able to not only understand the content, the text, if you are able to link the ChatGPT with the code, you can actually understand code, search the code, and write better code. So this is a big thing, actually. But the currently ChatGPT just linked with your repo. There's no kind of comprehension capability. So what we're doing here is a code comprehension agent. We want to start with the repo or even binary to generate do the code analysis, generate the architecture, and essentially we want to reverse the requirement. And then use these things to really understand whatever program you have, and then we can build this MCP kind of libraries for ChatGPT to do. And this thing can can have many interesting applications. We can, if you give me whatever app, we can use this approach plus this thing. We can re-implement this software automatically. And that can be very powerful things. If you are set up, you want to build something, following some kind of apps, you grab it, and then you can have your own version in 1 or 2 days. Right? That will be something amazing. So I think this will be a very interesting, different kind of agent we want to build. And I just want to share with everyone that these are, I think, the interesting and useful applications. But after building all the agents, now people are talking about next generation of agents. It's not an AI agent, it's more the genetic AI, right? Which is, I think, the kind of intermediate step somehow toward kind of AGI. So this brings a lot of, I think, the discussion, and the new research directions we want to try it out to see how can we build smarter agents, and the agents not only able to simulate the human expert, but whether they are able to discover knowledge, maintain knowledge, and learn new things, and even create new knowledge. So these are the things people really start to think about. So I think 2 weeks back, there are several papers talk about self-evolution of the agent. I think that is, the very important things and interesting things, but how can we potentially do that in a more systematic way? And how to bring this kind of more advanced learning, evolving capabilities into the security agent we're building. So these are the things we start to look into. But to answer this, it seems very difficult because what is AGI, what is intelligence? We don't really have the answer for that, right? So this triggered us about a very deep question I'm asking my team every day. So what is intelligence? People never have a kind of a deep thought about this. We're doing all this AI, doing all this agents, but we never question what exactly the intelligence about. Right? What are the things support us to give us the intelligence? Right? So these are the things I ask my kids every day. So they said, "Dad, you are crazy. I don't care what is intelligence. Just give me the Coke." Right? But so this is the diagram we came up after, I think, intensive discussion after 3 or 4 weeks recently. This did not come from any reference because after going through these kind of details about intelligence, there is long history literature in psychology, philosophy, and even the cognitive science. People are talking about different kind of intelligence, different kind of capabilities. I think the things I'm interested in is not just about definition. I want to understand what are the fundamental capabilities the human are having so that they can gradually to do more complicated tasks. And this thing actually we figure out many interesting kind of understanding. For example, perception is a very important capability. We have all this sensing, we have all the sensors, your eyes, your ears, your nose are all the sensors. But perception, how can we receive the information? And then you have all this attention to pick the useful information and use that. So these two each actually involve a lot of understanding about different kind of information processing and filtering and optimization so that you can quickly zoom into the right information and to do the reasoning and the plan. And so this, I think we figure out some of kind of important things which we are trying to borrow from the human brain. I think that is a very good source for us to bring this capability. And after that, then you can do learning, creation, problem solving, critical thinking. And this step, I think, is the more general or comprehensive kind of cognitive capability supported by each of these. So this circle is not drawn arbitrarily. Actually, there are many kind of theorem and the theory and the reference behind things. And then you can have all these things. And the interesting thing is that this everything is linked to a very interesting concept called 21st century skills, which is imposed by Singapore Ministry of Education because the government wants to train kids with all this nice capability. And which you think about, this is right? When you build an agent or robot, you want them to be a good citizen. And they need to understand this so that they can follow the protocol. And they can learn the things quickly and effectively. And they also have all this kind of culture, moral kind of understanding and actual understanding about the community. So this, I think, is actually very, very big stuff. And we don't just want to draw the picture. I think the more ambitious things we want to do is that how can we potentially build an agent come with this kind of capability? Right, so that is actually a very ambitious things, and we don't stop just by showing you diagram. We start working on this a little bit. So we start to really revisit this diagram, and we found that okay, these things are reasonable, but it has certain things like memory, short-term memory, long-term memory. But actually, long-term memory in the human brain, they have two different kind of long-term memory. One is called episodic memory, one is called semantic memory. Episodic memory is talking about the scenario, all these facts. Semantic memory is talking about your true understanding about the semantics of a certain thing, right? So you need to further divide these things into more detailed things. And here, all the planning, if you look at all these things, is actually mapped. Some of this basic capability here, they are not complete. So actually, we are trying to enhance this diagram so that we want to build a more comprehensive agent architecture. So these are kind of very ambitious things, and my kid told me that it's too big and you are not able to do it. So, but nevertheless, I think no harm to try. So the first thing we did is that we try to understand the capability of a human brain to bring the necessary components into the architecture. So the perception, attention, memory, planning, reasoning, reflection, and learning, these are the very good and necessary component we believe you need to have in the agentic AI or all the AGI things. And this thing is very important. The memory, I think human is, I think, a very important we have the memory, which is to have an understanding of the things in the current sets. And also you have the long-term memory so that you can turn certain things into from short-term memory to long-term memory and use it later. And more importantly, the memory is not simply store the facts. Actually, we store many of this very important high-level understanding about the facts, about the world, so that we can become more intelligent and more robust. And so this is, I think, the very important understanding we need to bring. Just not simply copy this memory idea, but bring the kind of more high-level thematic understanding into the memory so that you can become more intelligent. But nevertheless, this part, for me, I think, gave you the efficiency, not intelligence. Why I say so is because this process is trying to simulate human brains. And the human brain actually is only using 24, and we can do so many crazy things. But human brain, you have a child brain, you have adult brain, you have a security hacker's brain. And the child cannot do the hacking things, and even most of the adults cannot do the hacking things. because the hacker has certain knowledge, but all these three brains are similar. So this give you the efficiency, but not really give you the intelligence. So this is important to introducing the architecture, but to have intelligence, this is the things we're starting looking into, right? So I named this kind of deep think architecture, which essentially we borrow this very interesting kind of a concept from cognitive science. So this is called kind of sixth level of thinking. And it started with this kind of remember things. It's very easy to understand, right? When we learn things, we remember, but we don't understand. Like we want to recite all the poems, you can do that, but you never understand the deep meaning of the poems. And after you understand, that is a different level, and after that, you can apply it, right? So these are most of the things we can do reasonably well. But if you're looking at further, analysis, evaluate, create, these are more kind of expert, right? Like you have really the top expert, like a doctor, security expert. They can do the analysis. They just not just apply. They can understand. Okay, when you have certain things, I do some kind of simple statistical analysis. I can already become very good of certain things. And I think I give you one interesting, exciting. My PhD supervisor suddenly one day he told me he played the tennis. Then he told me, "Yeah, you need to start to train the kids with the butterfly move." That's why, because when you play tennis, right, you have all this kind of cross stroke. And he studied more than 30% of this plays in the tennis match about butterfly. And if you train the kids with more butterfly during their training time, and they will be better. And he showed me his son is in the kind of NCAA team, and he told the coach to do the simply every training have 30 minutes more butterfly training, and the team the ranking starting from 50 something, they move to 10 something, right? So he showed me this is a works. So now we start with asking the kids to do this. But this shows me it's a very simple kind of analysis skill. If you can have a more kind of global understanding about the problem and you do a little bit of analysis, you will become a better. Right? And then you can see, when you have the analysis, you can compare, evaluate, find a better solutions to solve this problem, and you can choose the better way. And the most, I think, advanced kind of capabilities is that after you become so experienced and so expert about certain things, you are start to think about how to create things. And these are the very important skill sets. We call it higher order thinking skills. And if people have these things, they will become a much better kind of expert in their domain, right? So what we want to learn, why I want to mention about this is actually the smart way to think. And if we are able to digitize this, automatically, somehow, in the agent, and the agent will become the super agent. So this is, I think, the more exciting things. If you can add this with efficient computation with the brain, I believe that is the better way to build the agent. And that is things actually we are now trying to experiment, right? And these things are not so abstract. We're thinking, for example, the decomposition is actually a very smart way to do this kind of analysis, right? So, but this is the kind of things we learned when we are the computer scientists. All the computation learning, we learned about abstraction, decomposition, algorithm. So these are all these kind of advanced skills. So if you are able to have all the digital kind of understanding about that smart thinking, and you can digitize that into certain algorithms, and then you have the intelligence. So this, I think, are the interesting things we are trying now, and this is about another aspect of knowledge, which I think the important thing within human brain is that the smart people is able to see the deep abstract semantics of certain things and put into the memory. So the structure and content in the memory is actually very, very important. If you can see the theorem, you can see kind of deep formula about problem, and you can easily solve all kind of these related problems, right? So the knowledge abstraction and the modeling actually is a very important capabilities and the skill sets the smart people have. And why I can see certain things, why the doctor can certainly understand based on all this phenomena, he can understand what is the problem with the patient, because he have all this kind of high-level understanding methods. Yes,
Sorry, I arrived late. So I missed most of the time. What are your agents? Are LLMs, are abstract agents? I'm pretty sure you said it before, but I wasn't clear.
I think this is the next generation of the agent architecture.
So you assume there are these agents?
Yes, yes, yes. So we don't care. You can, I think for me, language model is just a language component within brain. But you need to have all the other memory, all the things in order to, yeah. So that is why we are, yeah. So this is another part, and then this is knowledge. If you are able to abstract the word in a meaningful way and put this into the process, I think that is the better intelligent potential you can have. And this is another thing. We want to build high quality agent. And to do it, you need to have a high quality prompt, right? But prompt is not something straightforward. I think, I'm not sure how many of you have played with prompt with language model, right? You ask some question and then you found that the return result is not consistent, you have hallucination, you have like different time, you have different answers. Then this is because the language model or this agent is a completely different computation architecture compared with the traditional programming language. And we need to have a better way to build the prompt. And that is the reason, especially we want to, within the knowledge space, we want to have a more systematic way to apply into the prompt development so that we can have high quality prompt. And that is why we call it, we named this term called prompt way, right? So we want to build high quality prompt using the software engineering practice so that you can have high quality prompt and high quality knowledge. Then you can stay in the brain. And this is another thing, I don't have time to put slides. This is when you want to build the AGI or agentic AI, you need to have the safety and security support. So the security is one important thing, and we have been working on this. We started with the large language model security, but now we are working on all the agents attack. But this, for me, I think interesting things we summarize is that AI security, agentic AI security, is not simply kind of engineering stuff. It is more about understanding about the scams. If you think about all the things we're doing with large language model, you're trying to scam the large language model so that large language model will tell you not the things they're supposed to tell, but also do something they're supposed not to do. Right? So this is very much like the kind of human world. So after doing all this kind of scam research, we found that more advanced scam playbook are the important things we want to find out. But not only that, I think now I just have a new hypothesis about AI security or agent security is that all the adversary kind of attack to our agent is actually very much should be linked to the different intelligent capabilities. It should not just think I'm doing this kind of attack, but what we really believe is that we should examine the security and the security of agents based on the individual intelligence capability here, and how can we do the adversary attack for each of these. And that's, I think, is a more fundamental way to approach the agent security. And this is how the human world works, right? So it's not simply kind of knowledge model. You have also the trust, how to build the trust, how to break the trust, how to have all the access control of the agents. Also, all of this actually fundamentally boil down to the different kind of intelligence capability. And you can attack each of these, for example, perception. So these are the things we're doing, right? You do some kind of interpretation in the image, whether it can be visible or not visible, and you're doing the attack on the perception. And you can do all this attention. You can misalign the focus of this human expert to something else. He should look into the traffic, look into the traffic light, but then give something else, then this person suddenly focus on something else, then he missed the traffic light. So this is, I think, the right way to systematically look into the security of the AI agent. And then we already started working on this. I think we got a very interesting result, but there is actually a very big space to work on that, which is not straightforward. So that is about the security, and I think this is also something interesting. We found that after you build the agent, and then the agent will become black box. When you talk to a certain agent, you are not able to understand what this agent want to do or want to achieve. But you need to somehow interact the agent so that you need to do all this agent behavior. And after we start to think in this, we finally understand why we need to have the judges and the juries. Because most people, you will not review your true thoughts. And we can only judge you by the behavior. And then we use a kind of panel to decide whether you are a good guy or bad. Right? This will be the same thing for the agent, so that we need to have a way to collect and perform analysis on the agent behavior to understand what they are doing. And I talked so much about this, you may think, okay, this is too overwhelmed and too many information when any of this could be potentially useful, right? And to address that, this is, I think, the one of the things we're working on now. I want to bring all the ideas I mentioned, all these things, into a real setup. This is to do the kind of physical world kind of understanding. So we want to have a more semantic level understanding about the physical world. And probably you heard about this, doing this, the word model, right? Want to do this kind of, she calls it kind of visual intelligence. We are adopting a slightly different approach. And here we really want to use the multimodality model to map the physical world quickly with the semantics behind the concept, your laptop, your map, and all of this. And based on this, then we do the temporal reasoning and spatial reasoning about all these objects. And use that, we do the conception cognition understanding to really understand this is the seminar room, and we have an audience, we have all the kind of desk, the laptop, and we are doing this activity. And this give you more high-level understanding and robust understanding so that you can do it in a more robust way, apply the kind of knowledge in a more robust way. And then this knowledge is putting into this kind of human brain-like architecture so that the high-level semantics and efficient intelligence can then merge together to achieve kind of the good result. Right? So based on the initial evaluation, we developed some kind of autonomous driving system which can already beat SOTA, and it's more robust. I think these are the good results we are gradually able to achieve. But I think this is actually very, very interesting things worth exploring. I think last topic, I think this is something we are going. So the idea is that I mentioned that we are building this end-to-end coding agent to develop software. And suddenly we found that this idea could be adopted to the agents, the prompt development actually. So that potentially if you want to build the agent, we can review the same structure and generate a prompt automatically for you. And then that is kind of the ultimate intelligence potentially we can achieve. So this is, I think, another crazy idea. I got a very good student pushing to work on this, and we hope that we can have some results in the future. But the whole thing essentially, we want to learn. This is my last slide. So right, I call this name called brainery. It's a brain and binary, right? So we really want to bring all this kind of capability to support all the intelligence I showed in the earlier slide, and then it's able to make it intelligent and efficient. So this is, I think, the ambitious projects we are working on. But nevertheless, any of these ideas, if you could adopt into a particular agent design, I believe it will give you some benefit because this is the, I think, proven way of intelligence for human beings. And we hope that we can gradually copy and bring some of the ideas into the agent design. I think that would help us somehow to getting one step closer to that. Okay, so this is all, and I'm not doing all of this. I'm just presenting all the work done by the group of fascinating students back in Singapore, and we hope that we can keep discussing this and possibly collaborating either on the application side, or if you're interested, we could discuss more also on the agent design side. Okay, thank you very much. Yeah.
If I may ask, how do you evaluate the explanation with Agentic?
Sorry, that.
You know this agent that you said you were contacting in the beginning. That's your problem.
Oh, yeah. The real fix, yes.
How do you evaluate the explanations on both of these?
Oh, that is actually a very, very good question. When we have the root cause and the solution for the root cause, you can print this thing out when you do the analysis. And that is the concrete evidence you could compare with human behavior. And that gives you the kind of assurance that whether the agent is doing the reasonable logical reasoning about the bugs and the corresponding fixed solutions, which I believe is the general way to solve most of the, for example, the math problem. So that is why I'm now more happy about the solution.
And can I follow up with it?
Sure.
Have you got us in this work package that you showed? There's green strata of agents interacting together. Have you thought about like orchestration of these agents in code development, or is it more of a linear product?
Oh, yeah.
Where one gets the answer.
Okay.
Just,
I whether I can go back to the previous slide. Yeah. Okay. Maybe I think yes. So this, when we start planning this, we thought, okay, each of these could be a useful agent, and then you do the orchestration. But later, when we really start looking at the details of each of the agents, we found that even the requirement analysis agent, it is actually itself a multi-agent system. Why? Because if you're looking into all the definition of the software requirement engineering process, it involves software elicitation, software analysis, software documentation, and software verification. And all of this, each is an independent steps. And after we discussed this approach, we found that you need to actually have a working memory, and each of the agents need to monitor this working memory. Whenever you have something change, the different agents need to follow up and interact. This triggers us actually a lot of discussion and thoughts about all the agent design, because even within our brain, the different part of the brain are not working in a sequential way. Actually, they're all working together with your short-term memory. And I think the agents need to be like that in order to have the state-of-the-art information and do the right action at the right time. So that actually is a very interesting thing. And later, when I start to look into the MIT human brain course, then we found that actually different part of the human brain, they are highly connected. And when they are doing certain things, and different part of the brain are activated at the same time. So this is actually a very fundamental question that we need to address. It's just not about the agent. Of course, you have agents, multi-agent. You need to decide when you use what, right? If you have a more independent task, you can use the agent. You have more different things, you can separate them. But I think fundamentally the question is that when you do certain things, you have different kind of capability. How should you combine them and use them together on the given task? So that is actually unknown things yet for the human brain, but I think these are the things worth trying out. But very likely, I believe most of these sub-agents, they are talking to each other and working on this, the working memory simultaneously.
The last one. A lot of these, I guess, agents or models that you worked on, I think they rely on some version of few-shot learning. But as you've also thought of or already tested model context protocols, integrating MCPs into...
Yes, so we have quite a bit of research working on that. One thing is that we want to build this MCP for open source repository and provide them at MCP kind of libraries for the ChatGPT. So that is something why we're working on this reverse engineering task. But another, I think, interesting things we're looking at is the MCP protocol actually have a lot of security challenges. Because whatever things going to or going out from an agent, you need to understand the roles, scenario, context, and all the trust. I think that is actually much fine granularity than just a simple protocol. Yes or no, you have the simple authentication. Right? So, but people don't care that yet, but I believe that will be a very important topic we have to address very soon. Yeah. Thank you. Sure.
So you were very unhappy about data-driven approach and was persistent about this knowledge-driven approach, which I highly admire. I think this is the right way to go. I guess to break the question down to two. One is that what is really how do we really define what's the line between data and knowledge? Because knowledge at the end of the day is also information.
Right.
I guess the second part is it seems like AI still is not able to, you just give them kind of relatively raw data and give the output that you desire. But you still need the human to bridge this, as in people are scared that AI is going to replace human. But based on your presentation, human needs to learn first and then abstract this knowledge and then give to AI. Like AI seems not to be able to learn yet. It seems that type of input still needs to be entered by human beings.
Yeah,
is that
that are two excellent questions. Okay, and actually we have a heated discussion between me and my students. First, about this data or knowledge driven. We didn't really understand the big difference at the beginning, but gradually, I think we have. If you have ever read this book, Slow Think, Fast Think kind of book, you probably get this kind of idea. Data-driven approach, first, is a very important kind of, for me at least for now, is a very important perception capability to quickly understand certain things of the certain semantics of certain things. So that gives you kind of input semantic mapping capability. But how far you can go with it, how much intelligence you have in the large model, that are the things people can keep pushing on. But to a certain stage, you need to work on the semantic level in order to make it more efficient, more intelligent, or more robust. So I think the bridging of this raw data and the high-level semantic mapping, this is the power of the large model, which we cannot deny. If we don't have this, we cannot quickly understand whatever the text we have, whatever kind of multimodality information we have, right? So this is kind of, I think, the key role for the data-driven kind of model you can use and apply. But actually, even you have the high-level chain of thoughts, this is also data. And when you have enough this kind of high-quality COTs, you can also fine-tune a model to do this thing in an effortless way. It's like the human beings. When you become the expert of this, and now, like when you learn driving, right? After you get your driving license, you need to really be careful when you drive. But after 2 years, 3 years, you can drive with the phone, with the friend to chat, right? No problem. You can still drive perfectly. So that is slow think, fast think kind of a difference. If you are expert already, you don't do think. Large language model is kind of aggregation of this useful data so that they can quickly inference, effortless inference, but there's no guarantee. However, if you are already expert in a certain thing, your COT is good enough, you train with enough COT, even though it's fast thinking, you can still do it with fairly good accuracy. Right? So this is a kind of the gap. But fundamentally, if you want to have certain guarantee reasoning, any kind of evidence proof, you need to have this kind of slow thinking. You need to have this kind of evidence. So this is the kind of, I think, the understanding about the data-driven, knowledge-driven. So now actually we start to appreciate data-driven things because that gives you the quick way to do certain things. So this is kind of the things we will reflect recently. Second question is.
Just it sounds like human beings are still not replaceable.
Oh yes.
You still need the human brain to process and then spit out.
That is actually Yu Qiang, my postdoc, is here. So I push him we have built this crazy vulnerability detection agent, right? We are able to find 0 days. So now I ask him to do a follow-up task, whether we can build a COT of COT, so that we can create new COTs. We can combine and optimize different COT. So that is kind of a different skill set. So that's why when I show the diagram here, right? In this diagram. So we mentioned explicitly, so the creativity is a different capability. So we want to understand how the human is able to create new knowledge. And I believe may not be all, but certainly certain kind of creativity can be automated. This is the things I think we believe, because I'm doing research every day, I can think so many different ideas. If I can teach the agent how to create certain new topic ideas, I think the agent can learn. I don't say all the creativity can be done by automation, but certainly certain part of creativity can be done. Right. So this is, I think, the things we want to push the boundary, and I think this is actually the excitement we have. If you think about the human history, we have the language, we have the book, we have the library, we have the internet. This is all about knowledge propagation, knowledge digitization. But people never talk about, in the human literature, people never talk about knowledge creation yet. But now I think there is a possibility we can move for the knowledge creation automation. I think that is a very, very big thing. And that is why one of the key topic we want to drive now.
Thank you very much. Do you currently working on the specifically on jailbreaking method? Because I have this collection of 100 jailbreaking problems. I mean, actually, I'm building this Agentic AI safety information from them. This collection of jailbreaking problems currently I don't think work on GPT model. It works on a DeepSeek feature, but it's not working on GPT portal. We have, working on this jailbreaking methods.
Yes, we have actually a big team working on the different part of the AI security. As I mentioned, right, we started with direct jailbreak, and then now we are working on multi-conversational jailbreak. Yes, and also we start looking into not just the jailbreak of the model, we are looking at the agent level, because the model is just part of agent. I think the more important part is not about the model now. I think it's more about the agent. And when we talk about agents, I think the more important thing is to do the attack on each of this capability. So this is, I think, how our research is evolving. And then also, we want the jailbreaker also to be smart, so that you can do these things in the kind of self-evolving way. So you could actually, you have something working for this, you have something working for that. How can you borrow different ideas? Right? So this is how human, if you're doing the jailbreak yourself, right, you will definitely learn from all these kind of old tricks and apply in the new setup. So this kind of transfer learning, how can be done in a more efficient way. So these are all the things you could do actually. But essentially what we're doing is that you build an agent to do jailbreak. And this agent then you could think about, okay, what are the capabilities of this jailbreaker agent should have to make it more intelligent? All right, so this is actually why I think the AI is become more important than security, because you need to become the AI expert in order to build more advanced security solution.
Are you trying to attack specific components of instead you more attack the capabilities?
No, you could do both, right? You could attack the component, but I think fundamentally it's not about the component. Component for me is just the way the intelligence is implemented. So the true understanding is about the intelligence capability. I think that is more important for me.
Oh,
Yeah, I can.
Sure.
okay, well, let's say we stop at half past this.
I mean, it's a bit weird one, but every time I see like someone trying to replicate biology in computer science, I start thinking whether it's a good idea or not. And
Yeah.
because of the large language models and how bidirectional large language models operate, some are way better than one unidirectional in the back in the days, regardless. But have you thought about other approach that would make sense for this knowledge or AGI creation that would be that would, I guess, emerge? And again, I realize that in the absence of any better solution, it's always better to follow biology, right?
I have another talk I can give about this topic. We have another line of research we call Software Genome Project. Because I don't have the slide here, but we're trying to map between the code and DNA, and then you report to the kind of the chromosomes, and then you found that the human beings is amazing creature. You have your DNA, you have mRNA, you have your protein, and you have source code, you have compiler, you have binary. So the human beings is actually a self-contained computation machine. So this gave us a lot of kind of the insights about computation and the logics. And we are doing this. That is why why we name it Software Genome Project, because there is a human genome project try to understand different kind of functionality of different genes, right? We should understand different kind of computation capability of the software, and what are the things we can build on top of that. So actually, we have all this very interesting concept called software migration graph, software taxonomy, which is similar to the animal and plant taxonomy. So these are kind of concept borrowing is actually very much making sense, and we are applying it. And more excitingly, I feel that the AI research is become an inevitable evolution of human. Because if you think about the human evolution, you start with a single cell, gradually you have this more kind of structures, and then you have the brain, and the brain become bigger and bigger, you have more and more intelligence, right? I just visited the Natural Museum, Natural History Museum near the Imperial, and we saw the different how the human brain evolves, right, along the years. So I have the picture, I should put that here. And that is how the intelligence evolved. And what we are doing, the code is your body. And the large language model or the agent is your brain. And this is how the human evolved, and this is how the digital evolved in a very similar manner. And the large language model will appear no matter what. Now you see this is a destiny. And after that, you see the language part, but we want to bring more the kind of other part of the brain to have the so-called the kind of the intelligence we want. So this is a kind of the similarity and the analogy. Yes, I think this kind of research, you should just look into the human evolution history, and you just follow this kind of research in the computer science, and you can do many, many things. It's not just the kind of borrow ideas, but I think this is kind of destiny. You have to do it. And the human has been, after all this natural selection, is proven to be an effective, intelligent species in the planet, and we can achieve so many things, and agents will evolve in a similar manner. This is I think if you look at all the Turing Award winners, they discuss how they find all this, come up with the idea of a neural network, all these things. They all came from all this cognition science and human brain, all these studies. I think we just should follow, but they just the starting point, just the language part.